So welcome everyone to this week's Autonomy Talk. This week is a great pleasure to have with us Professor Ichiro Hasuo from the National Institute of Informatics in Tokyo, Japan. Ichiro agreed to give a talk, although it's pretty late in his time zone, and we're really excited about it. So Ichiro is not only a professor at NII, but also the research director of the JST Erato Mathematics for System Design project, and also the director for the Research Center for Mathematical Trust in Software and Systems. He received a PhD in computer science from Radboud University, Nijmegen in the Netherlands, working with Professor Bart Jacobs. And his research field is essentially software science, and his interests are around formal verification, mathematical and logical structures, integration of formal methods and testing, and applications to cyber-physical systems and systems with statistical machine learning components. Today, in particular, he's going to talk about proving safety of automated driving vehicles, a formalization of RSS with program logic. This is very exciting work I've been following offline, and I'm very happy to have Ichiro now live giving a talk about it, and that's why I give you the stage, Ichiro.
Thanks a lot, Jolie. And I have to say, this is the best introduction that I have received in my scientific life, scientific career. So thanks a lot for your wonderful. I mean, I don't think I deserve it, but anyway. So my name is Ichiro Hasuo. I work in Tokyo, and this is about I don't know how many of you have heard of formal verification, but I will also try to introduce that a little bit. So, but then that whole methodology of formal verification is applied to the safety of automated driving vehicles. So I'm gonna start with a very non-technical overview, something that I would give to my family members or my mom, for example. Probably, yeah, we'll see. But anyway, so this is the problem, right? We have been seeing the advancement of automated driving technologies, but it's not that those automated driving vehicles are running everywhere, on every street in the world. Why is that? Because the society is not yet ready to accept them on public roads. The society has to be convinced that those automated driving cars are safe enough to be accepted on public roads. And then the mainstream approaches to such safety assurance is either by statistical data. This is so-called the distance approach, like how many crashes, derailments after driving how many miles, right? But then probably a more fine-grained approach is by testing and simulation. So you have a list of test scenarios, and you say that this vehicle is safe enough if it passes all these test scenarios. But then, so these test-based approaches, they are hardly free from those criticisms. This ground is strong enough. Or can you explain why we should believe that these are safe? And especially for this approach, which is the mainstream in the current standardization efforts, it is hard to come to a social agreement about how extensive this test scenario set should be. So it's hard to agree on this question, and therefore setting an international safety standard has been quite non-trivial. But then, we've been talking about these testing approaches, right? Then if you know about formal verification, then it's a natural idea to try to think of its use. So why don't we turn to formal verification and write mathematical proofs for the safety of automated driving vehicles? It sounds good, right? This is definitely free from these criticisms. But then, if you try to do that seriously, then you immediately see the challenges. First, like each vehicle, each automated driving vehicle, it's such a massively complex system, and such vehicles are hard to mathematically model. And even more so if you think about the whole traffic system, where it's a massively like complex multi-agent system with complex interactions between agents, right? So the bottom line here is that formal verification is about writing a proof, right? Like writing a proof for a safety theorem. But to state a theorem and to prove it, you have to define all the notions that appear there in the theorem statement. And here, like the definition in mathematics amounts to system models in this formal verification settings. And what I'm saying here is that such system models, mathematical modeling of systems, is like almost impossible. But then, like, here comes this work by Shalev-Shwartz and like 2 other guys. They are machine learning professors in Jerusalem, but also they are I think they are founders of this rather big company, Mobileye. They sell like automated driving systems, hardware and software. But anyway, these machine learning professors and entrepreneurs, they came up with this methodology, which I find surprisingly logical. It's called responsibility-sensitive safety. I don't know, like perhaps some of you have read their paper, and like to put it nicely, their paper is rich. There are many ways you can read that paper, and there are many lessons that you can get from this paper. Like another, like perhaps a less nice way of saying that is that their paper is hard to understand. But anyway, like so indeed, like many people took out like different lessons from their paper, but this is the lesson that I took from, and this lesson is a logical one. So what RSS is about is this transition from left to right. On the left, you are seeing an end-to-end safety proof, like working all the way from the very basic, like first working principles of each system component, and then all the way up to the top level system level safety claims. And like I said that this is impossible because first, this like proof is so complicated that you don't reach the ultimate goal. That's one. But another big difficulty is that these operating principles that are like mathematical models of each component is often simply unavailable. Like if you have a black box component that you bought from some supplier, then you don't know how it works internally, right? That's one example. Another example is that if your car is using a machine learning component, which it will, then its decision rule is a huge matrix, right? Numeric matrix. And the logical analysis of such a massive numeric data is almost impossible. So you don't have system models, so you don't have any basis to start with. That's the difficulty. But then this methodology RSS, what it proposed is this simple, like clever way of like disregarding all the details. So like it proposed that we should ignore the internal working of individual vehicles. So we can we don't look into how each car works, but instead the methodology imposes those behavioral rules which are externally observable and checkable. These rules are called RSS rules. And then the proof is the distance is short, starting only from these behavioral rules. And then this, you see that the safety proof is a conditional one, right? So the safety claim is true on the assumption that each car complies with those behavioral rules called RSS rules. And they have found that this proof, this conditional proof, is in fact quite feasible. And here's an example. Here's an example. So this RSS rule, it has to be determined for each single driving scenario. And they studied this very simple scenario where the car in the rear has to avoid the crash from the rear crash. And then, in my opinion, so they studied this simple scenario, and in my opinion, this is essentially the only scenario that they dealt with in this paper, and also in the subsequent development of this RSS methodology. But anyway, so this RSS rule is it's interesting. It's nice to remember this structure because it will come up later. So an RSS rule is a pair of a logical condition and a control strategy. So this logical condition is called an RSS condition, and this control strategy is called proper response. And very intuitively, this logical condition means so it means its content is like this, like you can still escape if this condition is true. And in this case, this condition requires a certain inter-vehicle distance, which is natural, right? Like, to avoid collision from the rear, you have to have certain inter-vehicle distance. But the notable thing here is that this required distance is precisely given by this mathematical formula. But then an RSS rule also has got a specified proper response that is a control strategy. And here it is to brake at a certain rate within a certain response time. And the intuition here is that when you try to escape, use this strategy. And then the safety claim, to put it precisely, the safety claim is as follows. Any execution of this proper response from any state that satisfies this RSS condition A is collision-free. So, like if A is true, then you can still escape. And this is a specific concrete way of escaping. And this conditional safety lemma guarantees that it is indeed safe. Okay, so this was the example that they had. But then, like, we wanted to extend it. Like, we worked with Mazda, a Japanese car manufacturer, and then they came up with this challenge. So, like, can we also do this complicated scenario where like this is the ego vehicle, the subject vehicle. It has to change lanes and stop on the shoulder. Like in Japan, we drive on the left, so this is the shoulder. And then, but in doing that, it has to also avoid collision into these cars. And you can see that, first of all, like when you drive, then changing lanes is one of the most stressful moments, right? It's difficult. And indeed, for example, like to merge in front of this principal other vehicle, POV, like to merge in front of this guy, the subject vehicle may accelerate. But if it accelerates too much, then it may not be able to stop here, right? So like there are like many constraints at odds with each other, and it's therefore this is a complicated decision-making problem. And this, like what we did was to formalize this idea of RSS so that we can write complex proofs, and therefore we can handle these complicated driving scenarios. So like we started out with this original notion of RSS. And although, as I said, its basic idea is very logical, its logical content was not formalized yet. And that's what we did. We formalized its logical content in using this differential program logic. We call it DFHL. And this, like one good thing about a formal logical system is that it's often compositional, meaning that you can do divide and conquer. So in this case, it was the case as well. So this complex scenario, we can split it into smaller sub-scenarios and establish RSS rule safety proofs for each sub-scenario, smaller sub-scenario, and then later we can combine them into a single RSS rule for the whole scenario. And then this logical formalization, excuse me, and this logical formalization allowed us to also extend the RSS itself to something we call goal-aware RSS. It not only guarantees collision freedom, but also goal achievement, like safely arriving here. So, but by the way, I've been talking about formalization, right? Like, what is formalization? I mean, I'm sure like some of you are very familiar with that, but in case you are not, like essentially formalization is a shift from pen and paper proofs to software assisted proofs. So like, if you have like 3,000 paper, a 3,000 page proof, engineering, like in terms of engineering, this is useless because like who can check the validity of this massive proof, right? But then like nowadays in computer science, software science, also in mathematics, people are writing more proofs, especially those complicated ones in software. Then this software, there's an algorithm called proof checker. It can check the validity of this proof, very complicated, very long proof, by scanning it by symbolic means. So this is formalization, and this is what we did. So then, just briefly about technical contributions. So this is what we did, right? We defined this logical system called DFHL, and then we showed that we can use it for deriving rules and proving their safety. And differential program logic, it's an extension of Hoare logic. I don't know how many of you have seen Hoare logic. Hoare logic is a logical system for reasoning about properties of programs. So usually a Hoare logic is A, alpha, B. It doesn't have S. But A is a precondition, alpha is a program, and then B is a postcondition. And what it means is that like whenever you start an execution of this program alpha in a state that satisfies A, then on its termination, this postcondition B is true. So this is Hoare logic, and this is you can use it for proving the properties of programs. Then like we extended it to so that it can accommodate differential equations and also safety conditions. And here the idea is to have control strategies like like accelerate and brake kind of thing as this program alpha. Then A is a precondition. So like if you start executing this alpha when A is true, then after the execution, B has to be true, and this additional safety condition says that stipulates that S should be true all the time during the execution of alpha. So this is like, yeah, this is our logic. And I have to say, as a theoretical work, devising this logic is not, it's pretty much straightforward. It's nothing very novel. So for example, the combination of Hoare logic with differential equations, this is something that is like very nicely studied by Platzer, Andre Platzer, in his differential dynamic logic. So there's nothing too special about this combination, but so this rather simple extension of Hoare logic, we found that it's suited for our purpose. Yeah, okay. So then, let me tell you a little bit about this, the correspondence between this DFHL quadruple, like precondition, program, post-condition, and the safety condition. So this nicely corresponds to the structure of an RSS rule, right? So the RSS rule, as I said, consists of an RSS condition. So when A is true, you can still escape. And alpha is the control strategy that you should use to escape. And this is indeed, like, if you think about it, then this Hoare quadruple, DFHL quadruple, means what you require for those RSS rule. Like, if A is true, then you can execute alpha, then the execution is safe, the execution is collision-free, and moreover, at its end, you can guarantee this goal B. And this you can use to, like, this is what I already told you. You can decompose the whole scenario into smaller sub-scenarios. And this you can do by, essentially by this sequential composition rule, which is like, as you can see that it's pretty simple, right? Like, post condition is B for alpha, and B is at the same time a precondition for beta. Then for this sequential composition, like alpha and then beta, like you can merge these two quadruples and reason about its precondition and postcondition. And this simple logical rule is applied for the purpose of compositional rule derivation and compositional safety proof. Yeah, like I don't go into these details, but there's really nothing that is special here. It's pretty straightforward. So then, like, some further developments we worked on, okay, I will talk about this, but RSS rules can be used as a safety architecture. So this is something that I'm going to tell you about, like, soon. And then we also worked on the automated proof system, which is specialized for intersection scenarios. Okay, so then I'm gonna spend another 5 minutes or so about how we can use these techniques, logical technologies, in practice. So this is just to summarize our technical contribution. So this is the idea of RSS. We just assume certain behavior rules on each car, and then the safety proof is only up from those behavioral assumptions. And we formalized this idea, and now we can handle such complex driving scenarios. But okay, so perhaps I'm yet to address this big question. We are assuming that each car is compliant with these behavioral RSS rules, right? Is this assumption realistic? So this is the ecosystem, I would say proof-based ecosystem that is based on such contracts. So, these behavioral rules, they are like contracts. And I can imagine, we are, one way of using them is that, those rules, safety rules, RSS rules, they are announced by some regulation body or standardization body. Then, based on this announcement, each car claims they take their responsibility in complying with those rules. And then you can think of it as a traffic law. And that there are traffic laws. You probably know about you probably know their contents, and you would of course claim that you always comply with traffic laws, right? Reality aside. And this is a bit similar here. So these cars, they are indeed claiming that they comply with safety rules. Sometimes they may not, but then in that case, an accident happens, right? But then because of the safety proof, this conditional safety proof, so if everybody is compliant, then there is no collision. So therefore, by contraposition, if there's an accident, then it is guaranteed that there is some bad guy. There was someone who didn't comply with the rule. So this is some argument that you can use to for the purpose of liability attribution. So yes, so like what is the workflow of using those RSS rules as mathematical traffic laws? So like I already told you that these RSS rules, they have to be devised for each individual driving scenario. So it takes time. And like I don't foresee that this rule derivation and safety proof is fully automated. So like there will be some human efforts. But after some work, a rule is produced and its safety proof is produced for each individual driving scenario. And this rule and the safety proof can be used for many purposes. Like this is one usage that I already told you about, the attribution of liabilities. Like it can be used for the purpose of safety standards. This is something that is currently being pursued in the working group for IEEE, this IEEE standard. Safety verification in the sense that I already told you. Then naturally insurance company will be interested. But then, so one thing that I want to highlight is this usage in runtime monitoring. So like this actually, here I'm claiming that complying with these RSS rules is in fact quite straightforward. So the thing is that these RSS rules, like they can be straightforwardly retrofit as a safety envelope to any existing ADV, like automated driving vehicle controller. So it's like this. So assume that this advanced controller is given, right? Usually it's by a neural network or reinforcement learning, or like it's like the mixture of machine learning and optimization. And it's complex, and it's like the safety proof of this guy itself is impossible. But then you can like wrap this black box controller with a baseline controller and decision module. And here the point is that an RSS rule consisted of these two, right? The RSS condition, which tells whether you can still escape, and proper response. This is a specific control strategy to escape. And what you can do is to simply implement this control strategy, proper response, as a safety controller, baseline controller, and use this RSS condition as a decision module. And then more specifically, like as long as this A is robustly true, then like it doesn't harm to keep using this advanced controller because the situation is not safety critical yet. But once the margin for the truth of this condition A becomes thin, then you can consider switching to this baseline controller, and this baseline controller like executes this proper response. And then its safety is guaranteed. That's the conditional safety lemma. And here are some experiments. So like we are looking at 3 different controllers. This is without such safety envelope, like AC advanced controller alone. And this is safeguarded, but with the original RSS rule. And this original RSS rule only cares about collision avoidance. It doesn't care about reaching achieving the objective. And here we are using our goal achieving RSS safeguard. And let's look at how they behave. So here, like there was no collision, but the lane change was too abrupt, and we consider it dangerous. Here you see that that the color is changing, right? So the light green means that the car is the baseline controller is intervening. And in the end, so what is happening here is that like AC wants to change lanes, but since it's not safe, BC keeps kicking back. And therefore, like there was no danger of collision, but in the end, the car didn't make it to the shoulder. And in the case of our controller, now BC is intervening to slow down so that it can like merge after this guy. So in a sense, like, I mean, very intuitively, you can say that this goal-aware RSS rule has got like longer horizon, and it can like plan ahead so that it can achieve this goal. And here's another experiment. The first two controllers, they behave rather similarly. Both of them merge behind. But then an interesting thing here is that our safeguard actually accelerates the car. So it knows that like the car can accelerate and merge in front of this other vehicle. So like, it can act more boldly, but with a guaranteed safety. And here is a bit more sophisticated, like game-like demo for our technology. You see that the ego vehicle is safeguarded from time to time, right? This green thing. And then, like in this game, you as a player should find a dangerous scenario for this guy. And like that you can never win in this game, right? Because this guy, the safety of this guy is mathematically proven. Okay, so sorry, like I should wrap up. So there are like 2 minutes about the real world application. So, one thing is that like when we talk about advanced, like automated driving, like these two worlds are very different from each other. Like one is fixed route, like mobility as a service kind of deployment, and the other one is automated driving in consumer vehicles. And what is different, because like the main difference is that whether there is geofencing, and like whether we know the routes, whether we can have a good estimate of all the environmental uncertainties. Here we can have a good estimate, here we don't. So it is important that like at a certain stage, like the car says, hey, I cannot handle this situation. So it's called partial ODD. But in any case, like in either case, like it is reasonable to assume that we know, like we have some knowledge about the operating environment of the vehicle, so that we know like which driving scenarios the car will be in, and therefore we can prepare those RSS rules for those driving scenarios. And I told you that developing an RSS rule and doing a safety proof takes time and effort. Like I would say like 1 person month for each scenario. And probably we are looking at like hundreds or thousands of rules. So it takes time. But it is important here that like we don't have to wait for the full coverage of all the scenarios, because like as soon as we get one scenario covered, we can implement this RSS rule as an additional safeguard mechanism and cover more driven mileages by safety proofs. So this is therefore like this way the coverage by mathematical proofs can be gradually increased. And like after all, like I think like what we are looking here at what we are looking at here is the contrast between these two shapes of safety. Black box safety, in black box safety, the manufacturer just claims like it's safe, believe me, and you have to believe that. Or there's accountable and more transparent shape of safety where people or like in the society, they can like critically examine those safety claims. And when they do so, like my point is that they will use logical reasoning. And this is obviously the desirable shape of future that we are pursuing. So like if we think about it, then it's not only automated driving, right? All these like generative AI, like everything, like this destructive new IT, like information technologies that we are seeing, like it's like there are safety issues, like whether we can safely accept them in the society. It's always a question. And like what I have been showing today is that we can use proofs, mathematical proofs, for supporting such like safety assurance efforts. And here, like, traditionally, mathematical proofs are there to establish unquestionable truth, right? But then here, the mathematical proofs are rather different. Like, they are always conditional. And so mathematical proofs are like, in my opinion, they are like communication media that can articulate what contracts, what assumptions are needed to accept those new technologies to the society. So like this, as a logician, I see this, it's like a new business chance for logical and mathematical proofs, and I'm personally very excited about it. And I also believe that such power of logic is needed for human-centric human-centric reception of those new information technologies to the society. Sorry, okay, so I spoke too much, but thanks a lot for your attention.
Thank you very much, Ichiro, for the great talk. I think this is really interesting. So there are some questions in the chat. So feel free to keep writing in the chat and I will read the questions for you, or simply unmute yourself and ask. So we'll start with the question from Subrata, who's asking, how are insurance companies aware of the models adopted to build into their system for a claim settlement? Or if I can generalize the question, how do you envision the process of interacting with insurance companies? Who knows what in this process? I think this is a bit the question.
So okay, so there is one easy answer and one more ambitious answer. The easy answer is that you can imagine, if people can if people can agree that, for example, this logical safety envelope mechanism is indeed effective, then you can imagine that insurance companies, they prefer those logically safeguarded cars, right? So they can perhaps have some premium. I'm not too sure about the English, reduced fee for those logically safeguarded cars. So that's the easy answer. The more ambitious answer is that, well, actually, I'm not a specialist in the industrial developments, but I see that insurance companies are trying to play very active roles in this automated driving ecosystem. For example, for an automated driving vehicle, usually there is a safety driver in the car or somewhere remote. There's someone in the remote location, it is remotely monitoring this safety car. And such, this is business chance, right? Who runs this remote monitoring spot? And I know that some insurance companies are eagerly trying to make business out of this. So therefore, so I think what I'm trying to say is that insurance companies, they are in general active players in this ecosystem. And for them to, if this logical methodology is a key enabler to the real world deployment of automated driving technologies, then naturally they will be interested. That's more ambitious answer. Thanks.
Thank you, Ichiro. This is a great answer. I think I really resonate a lot with this vision. So I think then you showed some case studies, and Subrata was curious about, is there a common certification available for the models adopted in the particular cases you show?
You mean particular cases like these ones?
Yeah, I think so. Yes.
Yeah, certification. Okay, so I'm still trying to. Subrata, feel free to speak up, but I'm not sure what you mean by certification. But like my naive answer is that. Okay, please go ahead.
Yes, Professor. What I understand from your very nice talk is that to accept this system, because what we are trying to prove here is that we have developed some mathematical models based on which we are claiming that yes, the autonomous system is safe on the roads, given all the boundary conditions and the safety rules of the authorities and so and so. So the question is there any particular certification available for this particular model sort of a scenario for the ecosystem to accept that yes, within this particular model or models, then the whole system would function, and then whatever is the process of accepting it, be it insurance, be it near misses, be anything connected to the ecosystem of this autonomous driving?
Yeah. Thanks a lot for your very, very, very important question. And then the answer, again, the quick answer is not yet. Like there's no certification or there's no certification process. And this is something that this working group in the IEEE working group for IEEE 2846, like there are like most major players in this field are in this working group, like Waymo, like Waymo, Zoox, and others. But so like okay, so my quick answer is that there is no such ecosystem yet. But so I believe in the value of this mathematical, like proof-based approach, because like in the current situation, especially about the standardization, like making say international safety standards, is that like people don't know like what is enough to accept. Yeah, and then like here, like we are presenting mathematical proofs as something that covers some aspect of this safety assurance. And here I have to be very clear that it only covers a certain aspect, namely the decision-making part of the automated driving. For example, like it doesn't deal with perception uncertainties, like whether like a person is correctly recognized as a person, or it can be like incorrectly recognized as a plastic bag, for example. Like this issue is not addressed. Another thing that is not addressed is the actual actuation, right? So even if the computer says like the computer's decision is right, it can be wrongly implemented, and the car may like act in a different manner. So this is something that we don't cover, but we also believe that separation of concern is important, and at least we believe that for decision making, this is one possibility, viable possibility. Yeah, thanks.
Thank you, Professor.
Thanks.
Thank you, Subrata, for the questions. And then there is another question from Anna Lukina. Can this compositional approach potentially help recover guarantees faster without the need to re-verify the complete scenarios from scratch if one sub-scenario does not achieve the sub-goal? For instance, the preconditions change slightly and needs to be replanned on the fly.
Yeah, a very good question. Thanks, Anna, and nice to see you, Anna. Hey, so can be faster, yes, and then on the fly. So there's another thing that I like the use of how this works. One moment. So it's getting a bit late and I'm feeling a bit dizzy, but I will should be all right for the coming 10 minutes. Anyway, so this finding a rule and doing a safety proof. It is done offline. So before the car starts running, and what the car does is just to execute this safety architecture. So a good thing about it is that like there's no heavy lifting. I mean, computational heavy lifting, right? And it's not that the car should do like theorem proving while running. It just have to check the validity of this condition and execute this proper response if needed. So that's one thing. But then, but that said, one minute, if the sub does not achieve the sub goal.
Yeah, so maybe, for example, like you mentioned, the actuators don't really work properly, and I know you don't address that, but let's say that we managed to generate a new plan for the sub-scenario, and now we want to, again, give guarantees for the sub-scenario. Do we have to recompute everything and go, let's say, offline completely, or we can just recompute this part and the rest of the sub-scenarios are still safe and we can retain the guarantees?
Yeah, that's a very important one, actually. And it's related to this one, like nested safeguards. So here, like, okay, so I'm not too sure whether I'm answering your question, but let me still speak about this. So here we are looking at like two rules used as safeguards in a nested manner. And this we do typically for the purpose of graceful degradation. So like out of these two rules, yeah, like the first one, it's got stronger environmental assumption and stronger guarantee. So like, for example, the other cars maintain the velocity. That's the stronger assumption. And then therefore I can reach the shoulder. That's the stronger guarantee. But then if this stronger assumption turns out to be false, then we will rely on this second rule that assumes less and guarantees less. And typically, this weaker guarantee means that we give up goal achievement, like reaching the shoulder, we give up that, but still we maintain collision avoidance. I'm not sure whether I'm answering your question or not, but
No, but this is very useful. Thank you. So this hierarchy can be already quite helpful there.
Yeah. So that's, and like in the end, the problem is the main problem here is how to deal with environmental uncertainties, right?
Yes.
The real world uncertainties, and then like here we are, yes. In a sense, we are doing this best effort approach. Yeah, indeed, we are doing proofs, but at the same time, we are doing best effort approaches in the sense that we have this like different levels of assumptions.
Yeah. Thank you.
Thanks, Anna.
Thank you very much, Anna, for the question. And with this, I think we can let Ichiro go to sleep for a well-deserved night. Thank you very much, Ichiro. It was a great talk, and I'm excited to see where this goes in the future.
Thanks a lot, Joe.
Really appreciate it.
Thank you.
Thank you.
And thank you, everyone, for attending, and see you all next week for the next episode of Autonomy Talks. Take care.
So,
Bye-bye.
see you.